On November 29th, 2025, an object from deep interstellar space slipped to within 29 million kilometers of our sun. Small, dark, almost silent. And yet, for the first time, our instruments caught something we were never supposed to see: heat from the inside. At first, the data looked like noise, a faint rise in infrared flux, a thin whisper in the background of a crowded sky. But when teams cross-checked readings from ground-based telescopes and space-based infrared sensors, the pattern held. 3I Atlas was not just reflecting sunlight. A part of it seemed warm. That matters now because our window is closing. In a matter of weeks, 3I Atlas will drop below the sensitivity of our best instruments. The angle between the sun and the object will push it into a glare that even JBLUS struggles to see past. Budgets for follow-up campaigns are still waiting on approvals. Observatories are overbooked, and a rare interstellar visitor is already fading into the dark. The anomaly is simple to describe and hard to explain. The new heat signatures don't match a single known profile for a comet, an asteroid, or a fragment of frozen dust. Instead of cooling smoothly, its inner regions flicker. Localized hotspots appear and vanish. The modeled odds of this thermal pattern, being just random ice and rock, sit near 1 in 20,000. Scientists argue. Models are rewritten. Some quietly ask the question they're not supposed to ask out loud. Before we go deeper, hit like, subscribe, and tell me where you're listening from. Because this story is still unfolding. And so we follow the heat, and we follow the odds. This is 3I Atlas, what the new heat signatures reveal about its inner core. This is not science fiction. This is November 2025. Chapter 1. September 2nd, 2025. The first warm echo. September 2nd, 2025, began like any other day in the back rooms of infrared astronomy. Technicians checked calibration files, grad students sorted through nightly data dumps, and somewhere in a mid-sized facility in Chile, an automated pipeline flagged an anomaly. The object was already known. Designated 3I Atlas after its discovery path through the Asteroid Terrestrial Impact Last Alert System Survey Network, it had been tracked since late August as it carved its hyperbolic arc through the inner solar system. Hyperbolic meant interstellar. Hyperbolic meant it didn't belong to the sun. It came from somewhere else, and after its brief encounter with our star, it would return to the cold between worlds, never to swing back. Objects like this are rare. Onae Oumuamua made headlines in 2017. Toi Borisov followed in 2019, a comet with a familiar coma and tail that looked almost comforting in its ordinariness. 3I Atlas was the third confirmed visitor from beyond. And unlike its predecessors, it arrived during an era when our instruments had grown sharper, our networks faster, and our models more sophisticated. But sophistication has a price. It makes us sensitive to discrepancies we would have missed a decade ago. The pipeline that flagged 3I Atlas on September 2nd was designed to compare brightness curves. It watched how objects heated and cooled as they moved relative to the sun, cross-referencing their observed thermal emission against predicted models. Most of the time, the predictions held. Asteroids warmed in sunlight, cooled in shadow, their surfaces radiating away absorbed energy in smooth, predictable curves dictated by their spin, their composition, their shape. 3I Atlas did not follow the curve. The first hint came from a mid-infrared array, a cluster of ground-based telescopes in the Atacama Desert, optimized for thermal wavelengths. At a distance of roughly 47 million kilometers from the sun, 3I Atlas should have exhibited a surface temperature in the range of 210 to 230 Kelvin, depending on its albedo and rotation. The reflected sunlight component was measurable, albeit faint. But when astronomers subtracted that reflected component from the total signal, they found an excess, a thermal excess. The object was emitting more infrared radiation than the sun's heating alone could explain. At first, no one trusted it. Infrared astronomy is a delicate art. Atmospheric water vapor, instrumental drift, scattered light from nearby stars, even the thermal glow of the telescope itself can contaminate a signal. The team ran diagnostics. They recalibrated. They checked whether a background galaxy or a faint foreground star might be polluting the field. The excess remained. On September 3rd, a small satellite radiometer in low Earth orbit, originally tasked with monitoring Earth's radiation budget, was quietly repurposed. Its operators angled it toward the coordinates of 3 Atlas during a brief window, when the object passed through the satellite's narrow field of regard. The satellite's bolometers, sensitive to mid and far infrared wavelengths, locked onto the speck of light and measured its spectrum. The result came back within hours. The satellite confirmed the ground-based observation. 3 Atlas was warmer than it should be. Not dramatically so, perhaps 3 to 5 degrees Kelvin above the expected equilibrium temperature, but consistently, measurably, undeniably warmer. 3 to 5 degrees may not sound like much, but in the vacuum of space, where heat has nowhere to go except through radiation, every degree matters. Thermal models for inert bodies, rocks, ice, dust, predict temperatures with high precision. You input the distance from the sun, the object's size and shape, its surface reflectivity, its rotation period. The equations are well understood. They've been tested on thousands of asteroids, dozens of comets, every moon and planet we visited. And yet here was 3E Atlas, a visitor from interstellar night, refusing to cool the way it should. The teams began to ask the next question: where is the heat coming from? The simplest explanation is always sunlight. Perhaps the object had an unusual shape, with deep craters or reflective facets that trapped and re-radiated solar energy in unexpected ways. Perhaps its rotation was slow, allowing one hemisphere to bake while the other froze, creating asymmetries in the thermal profile. But the data didn't support that. 3. Atlas rotated every 8.3 hours, fast enough to prevent extreme temperature gradients. Its shape, inferred from light curve variations, appeared relatively regular, elongated, yes, but not grotesquely so. No hidden pockets where sunlight could hide. Another possibility: outgassing. Comets warm as they approach the sun, and volatile ices, water, carbon dioxide, methane, sublimate from the surface, carrying away heat in the process. But the same outgassing also releases dust and gas, creating the characteristic coma and tail that make comets so visually striking. Surveys specifically look for signs of a coma around 3 Atlas. They found none. No expanding cloud. No tail, just a point of light, sharp and solitary. Some suggested subsurface outgassing, jets venting from beneath a dust mantle, invisible to optical telescopes, but detectable in the infrared. This had precedent. The Rosetta mission to Comet 67P Churyumov-Gerasimenko revealed that comets could harbor active regions hidden beneath insulating layers, releasing gas through narrow fissures. If 3 Atlas had such vents, they might warm the surrounding material without producing a visible coma. Thermal models were hastily constructed. Researchers input layered structures: a dusty outer shell, a porous icy mantle, localized vents. They tuned thermal conductivities, sublimation rates, the depths of insulating layers. Some combinations came close to matching the observed temperature, but every model that fit the heat also predicted detectable gas emission, carbon monoxide, water vapor, something, and spectrometers saw nothing. The models that fit the temperature didn't match the chemistry. The models that matched the chemistry didn't fit the temperature. By the evening of September 2nd, a quiet unease settled over the research groups. The data was clean. The instruments were calibrated. And 3I, Atlas, this dark visitor from the space between stars, was carrying a warmth that refused to conform to the rules written for objects born in our own solar neighborhood. One researcher, a veteran of the Cassini mission, who had spent years unraveling the thermal behavior of Saturn's icy moons, voiced the uncomfortable thought that others were already thinking. What if the heat isn't coming from the outside? She said. What if it's coming from within? Internal heat sources are not exotic in the solar system. Earth's core is molten, heated by the decay of radioactive isotopes accumulated during the planet's formation 4.5 billion years ago. Jupiter's moon Io is the most volcanically active body in the solar system, its interior kneaded and stretched by tidal forces from its giant parent. Even small bodies can harbor internal heat if they contain enough radioactive elements, or if they've recently experienced a collision that converted kinetic energy into warmth. But 3 Atlas was small, perhaps a few hundred meters across, possibly a kilometer at most. It had no parent planet to tug on it, no recent collision history we could detect, and the amount of radioactive material needed to produce a measurable thermal excess in such a small body would be staggering, far beyond the concentrations found in ordinary asteroids or comets. The team pulled up archival data from other small bodies. They compared 3I Atlas to near-Earth asteroids, to Kuiper Belt objects, to fragments of disrupted comets. None showed this kind of internal warmth at this size and distance from the Sun. They ran the numbers. If the heat source was radioactive decay, the object would need to be enriched in isotopes like uranium-238, thorium-232, potassium-40 at levels tens to hundreds of times higher than any known natural accumulation. Possible, in theory. Implausible, in practice. If the heat source was tidal, there was no tidal mechanism. 3 Atlas orbited nothing. If the heat source was chemical, exothermic reactions within a complex mixture of ices and organics, then why hadn't it exhausted itself during the millions or billions of years the object had spent coasting through the interstellar medium? Each explanation required stacking improbability upon improbability, and so the unease deepened. On the evening of September 2nd, a senior astronomer sent a carefully worded email to a handful of colleagues at other institutions. The subject line read, "Anomalous thermal signature in 3E Atlas. Request for independent verification." The email outlined the observations, the cross-checks, the failed attempts to fit standard models. It ended with a single line. "We may be looking at something we've never seen before." Within hours, replies began to arrive. Some offered to repurpose their own instruments. Others requested raw data files for their own analysis. A few expressed skepticism, suggesting instrumental artifacts or overlooked systematic errors. But no one dismissed it outright, because the data was there. The warm echo was real. And somewhere in the cold dark of the solar system, a small object from beyond carried a heat that shouldn't exist. The first warm echo had been heard. And now, the question was no longer whether it was real. The question was, what does it mean? September 2nd, 2025, marked the beginning of a race. A race to understand, to observe, to capture as much information as possible before 3 Atlas slipped beyond the reach of our instruments. Already, trajectory analysts were calculating the geometry. The object's path would carry it around the Sun and back out toward interstellar space. In a few months, its distance and angle relative to Earth would make further observations nearly impossible. If there were answers to be found, they would have to be found quickly. And so, the instruments turned. Observatories began to reschedule. Proposals for emergency observation time were drafted. Scientists who had never met began to collaborate, pooling expertise from planetary science, cometary physics, thermal modeling, and spectroscopy. The warm echo had been heard. The first whisper from the core of 3 Atlas. And deep in the data streams, in the stacked images and the processed spectra, something waited to be understood. Something that did not fit the stories we tell ourselves about rocks and ice wandering through the night. This is not science fiction. This is September 2025. Chapter 2. September 4th, 2025. A core that refuses to cool. By September 4th, the quiet murmur of the initial detection had escalated into something close to urgency. Word spread through the astronomy community in the way that interesting anomalies always do. Not through press releases or formal announcements, but through private messages, shared data files, late-night phone calls between colleagues who trusted each other's judgment. The thermal excess was confirmed. Multiple independent groups, using different instruments and different analysis pipelines, arrived at the same conclusion. 3I Atlas was too warm. And the warmth appeared to originate not from its surface, but from somewhere deeper. Thermal modeling groups around the world began to mobilize. These were researchers who specialized in the physics of heat, how it flows through rock and ice, how it radiates into space, how it responds to changes in sunlight and rotation. They built computer simulations that treated celestial objects as collections of tiny cells, each with its own temperature, its own thermal conductivity, its own capacity to absorb or emit energy. The goal was simple: construct a digital twin of 3I Atlas, input the known parameters, its size, its distance from the sun, its rotation rate, and see if any combination of material properties could reproduce the observed thermal signature. They started with the simplest models: a solid rocky core, perhaps with a thin dust layer on the surface. The simulation ran in seconds. The result was immediate and clear: too cold. A bare rocky surface would radiate heat efficiently, reaching equilibrium far below the observed temperature. They tried ice. Water ice, carbon dioxide ice, methane ice, mixtures of all three. Ice is a better insulator than rock, trapping heat beneath the surface. But it's also highly reflective, bouncing sunlight away before it can be absorbed. And it sublimates, turning directly from solid to gas, a process that cools the surface dramatically. The models ran. Temperatures rose slightly, but not enough. And every icy model predicted gas emission that wasn't seen. They tried layered structures. A rocky core, wrapped in ice, wrapped in a dusty mantle. The dust would insulate the ice, slowing sublimation. The ice would insulate the rock, trapping whatever internal heat might exist. These models were more complex, requiring assumptions about layer thicknesses, porosities, thermal contact between materials. Some combinations came close. A thick dust mantle over a warm rocky core could, under very specific conditions, produce a thermal signature roughly matching the observations. But very specific conditions was a red flag. The universe is full of variety. Asteroids and comets come in countless shapes, sizes, and compositions. The fact that 3I Atlas required such a finely tuned structure to explain its warmth suggested that something unusual was happening. And then there was the cooling problem. Thermal inertia, the tendency of an object to resist changes in temperature, depends on its material properties and its size. Small objects cool quickly. Large objects cool slowly. A pebble left in the sun heats up fast and cools down fast. A boulder takes longer on both counts. 3I Atlas was small. Estimates from its brightness and distance suggested a size somewhere between a few hundred meters and perhaps a kilometer. At that scale, thermal models predicted it should equilibrate with its environment on timescales of hours to days. If it had been heated by some transient event, a collision, a burst of solar radiation, a brief episode of outgassing, it should have cooled back down to equilibrium within a week or two. But 3I Atlas had been under observation for weeks, and its core temperature, as inferred from the infrared excess, remained stubbornly elevated. On September 4th, a team from the Jet Propulsion Laboratory in Pasadena ran a systematic parameter sweep. They fed their thermal model thousands of different combinations of core composition, mantle thickness, surface roughness, thermal conductivity, and internal heat production. The simulation took hours, running on a cluster of high-performance computing nodes normally reserved for Mars mission planning. The results came back in the form of a probability distribution. For each combination of input parameters, the model calculated how closely the predicted thermal signature matched the observed one. The goal was to find a region of parameter space, a set of plausible conditions, where the match was good. What they found instead was a narrow spike. Only a tiny fraction of the parameter space, less than 0.005%, produced a reasonable fit to the data. And even within that narrow spike, the models predicted cooling rates faster than what was observed. In other words, even the best fit models suggested that 3I Atlas should be cooler than it was. The lead scientist on the project, a soft-spoken physicist who had spent 2 decades modeling heat flow on Mars, stared at the distribution and said quietly, "This doesn't make sense." One of the younger researchers, less encumbered by the weight of experience, offered a suggestion. What if it's not cooling because it's being heated? The room went silent. Heated by what? Someone asked. The young researcher shrugged. I don't know. But if the core is staying warm, something has to be putting energy in. Otherwise, it violates thermodynamics. Nimyi. They all knew this, of course. Energy doesn't appear from nowhere. If 3I Atlas was maintaining a stable thermal excess over weeks, some process had to be supplying that energy at roughly the same rate it was being lost to space. The list of possibilities was short. Radioactive decay, chemical reactions, mechanical friction, or something else. Radioactive decay was the easiest to model. They calculated the isotopic abundances needed to produce the observed heat flux. The numbers were absurd. 3I Atlas would need to be composed almost entirely of uranium and thorium, with concentrations thousands of times higher than any known meteorite. Such an object could not form naturally in any stellar environment we understand. Chemical reactions were harder to rule out. Certain mixtures of organic compounds can release heat when they polymerize or oxidize. Some ices, when mixed and compressed, undergo exothermic phase transitions. But these reactions are self-limiting. They consume their fuel and stop. For 3I Atlas to maintain its warmth for weeks, the reactions would need to be extraordinarily slow and extraordinarily efficient, releasing energy at just the right rate to balance radiative losses. Possible, perhaps. But again, it required fine-tuning. It required conditions that seemed unlikely to arise by chance. Mechanical friction, tidal heating, rotational stress was out of the question. There was no external force to create friction. 3I Atlas was alone, unbound, free-floating. And then there was something else. No one wanted to say it explicitly. Not yet. But the thought lingered in the room like a faint smell you can't quite identify. What if the heat wasn't natural? What if 3I Atlas contained something that was designed to stay warm? The scientist from JPL shook her head. We're not there yet. Let's keep looking for natural explanations. There's a lot of parameter space we haven't explored. Which? She was right, of course. Science works by exhausting the simple explanations before considering the extraordinary ones. And they hadn't exhausted the simple explanations. Not yet. But the window was narrowing. Observing time was precious, and 3I Atlas was moving. Every day it traveled farther from Earth, its brightness dimming, its signal weakening. Soon, only the most powerful telescopes would be able to track it. And eventually, not even they would suffice. Meanwhile, comparisons were being drawn to past missions. The European Space Agency's Rosetta mission had spent 2 years orbiting Comet 67P, mapping its surface, measuring its temperature, analyzing its outgassing. Rosetta found that comets are far more complex than the old dirty snowball model suggested. They have layered structures, regional variations, active and inactive areas. They harbor organic molecules, complex ices, even prebiotic chemistry. But Rosetta never found a comet that stayed warm without outgassing. It never found heat without a visible source. 3I Atlas was different. The team pulled data from other missions as well. The Mars Science Laboratories rover, Curiosity, carried an instrument called ChemChem that used laser pulses to vaporize tiny spots on Martian rocks, analyzing the resulting plasma to determine composition. Later, the Mars 2020 mission's Perseverance rover brought Pixel and Sherlock, instruments that could identify minerals and organic molecules at microscopic scales. The techniques were different from astronomical observations, but the principle was the same. Look closer. Examine the fine details. Don't trust assumptions. If only they could get that close to 3I Atlas. But they couldn't. Not yet. Not without a spacecraft, and spacecraft take years to build and launch. 3I Atlas would be gone long before any probe could reach it. So they worked with what they had. Long-distance observations. Photons gathered by mirrors and lenses. Split into spectra, counted by sensors, processed by algorithms. On September 4th, as the thermal modeling groups struggled with their simulations, another team made a different kind of discovery. They were looking at the time variability of the infrared excess. Thermal emission isn't always constant. Objects rotate, exposing different sides to the sun and to our telescopes. Surfaces have different emissivities. Some areas radiate heat more efficiently than others. By tracking how the thermal signal changed over time, You could infer details about the object's shape, rotation, and surface properties. 3i, Atlas rotated every 8.3 hours. Its light curve, the graph of brightness versus time, showed a clear periodic variation, confirming the rotation. But when the team looked at the infrared light curve separately from the visible light curve, they found something unexpected. The infrared signal had its own variation, a subtle rise and fall that didn't quite sync with the rotation period. At first, they thought it was noise, atmospheric turbulence, instrumental jitter, something in the data pipeline. But after carefully filtering and stacking multiple nights of observations, the pattern persisted. The core wasn't uniformly warm. It had structure. The excess heat appeared to come from specific regions, hotspots, that brightened and dimmed on timescales slightly offset from the overall rotation. It was as if parts of the interior were warmer than others, and as the object spun, those warm regions swept in and out of view. This was new. This was unexpected. And this was extremely difficult to explain with passive thermal models. If the heat source was radioactive decay, it should be evenly distributed, or at least roughly so. Radioactive elements are mixed into the bulk material when an object forms. You don't get concentrated hotspots unless something preferentially sorted and concentrated those elements, a process that requires geological activity, melting, differentiation. But 3i Atlas was tiny, too small to have ever melted, too small to have differentiated into core and mantle the way planets do. If the heat source was chemical, why would reactions be localized? Chemical mixtures are stirred, shaken, blended by impacts and collisions over eons. Again, you wouldn't expect sharp, persistent hotspots, unless something organized them, unless something structured them. The team lead, an astronomer who had worked on the Spitzer Space Telescope mission, sat back in her chair and said quietly, "This looks like plumbing." The room went still. "What do you mean?" someone asked. "I mean," she said slowly, "this looks like there are channels, pathways, heat being generated in one place and transported to another, or heat being stored in reservoirs and released in cycles. It's not random. It's organized." Another silence. Longer this time. "Comets have that," someone pointed out. "Subsurface vents, preferential pathways for gas flow." "Comets also have comet," the team lead replied. 3i Atlas doesn't. "What if the vents are clogged? Then where's the heat going? If the gas can't escape, the pressure builds, the temperature rises, and eventually something gives. We'd see an outburst. We'd see activity." No one had a good answer. The odds were beginning to stack. Each observation, each model, each comparison to known objects added another layer of improbability. Taken individually, any one anomaly could be explained. A warm core? Maybe exotic composition. Localized hotspots? Maybe unusual internal structure. Stable heat over weeks. Maybe slow chemical reactions. But all of them together? The combination was vanishingly rare. A statistician on the team ran a Monte Carlo simulation. She started with a population of 1 million randomly generated objects, each with randomized composition, structure, and thermal properties drawn from observed distributions of asteroids, comets, and interstellar bodies. Then she asked, how many of these random objects would produce a thermal signature similar to 3 Atlas? The simulation ran overnight. In the morning, the answer came back. 47 out of 1 million. Roughly 1 in 20,000. Those were the odds of encountering an object like 3 Atlas by pure chance, if all you assumed was natural processes and random variation. 1 in 20,000. Not impossible. Rare things happen. The universe is vast, and over cosmic timescales, even the improbable becomes inevitable. But still, 1 in 20,000. The number circulated quietly through the research groups. No one published it. No one announced it. But everyone knew it. And everyone knew what it implied. On the evening of September 4th, an informal meeting was convened over a video call. Representatives from NASA, the European Space Agency, the Japanese Space Agency, JAXA, and several major universities joined. The agenda was simple. decide whether to escalate. Escalation meant formal observation proposals. It meant requesting emergency time on flagship telescopes, like the Hubble Space Telescope and the James Webb Space Telescope. It meant briefing agency leadership, preparing reports, potentially informing government science advisors. Escalation was not taken lightly. Observatory time is precious and oversubscribed. Every hour spent observing 3I Atlas is an hour not spent on scheduled science. Exoplanet surveys, galaxy evolution studies, supernova follow-ups. Researchers fight for time, and asking them to step aside is asking them to sacrifice their own careers. But the consensus was forming. Whatever 3I Atlas was, it was not ordinary. It might be naturally extraordinary, a fluke of composition and structure that defied easy modeling. Or it might be something else. Either way, it was worth a closer look. The call ended with an agreement. Proposals would be submitted within 48 hours. Coordinated observations across multiple wavelengths, optical, infrared, radio, would begin as soon as slots could be arranged. And quietly, carefully, someone would start drafting a contingency plan, just in case the thermal signature didn't stabilize. Just in case it got stranger. Just in case the thing they were looking at was not a rock. September 4th, 2025. The core that refuses to cool. The heat that shouldn't be there. And a set of odds that made everyone uncomfortable. 1 in 20,000. This is not science fiction. This is September 2025. Chapter 3. September 10th, 2025. The instruments turned. September 10th, 2025. Arrived with the weight of decisions already made. Behind the scenes, in the administrative corridors of space agencies and observatory boards, the machinery of science had shifted into an unfamiliar gear. Emergency observation requests had been filed, reviewed, and, remarkably, approved. This didn't happen often. Observatory time is currency in astronomy. It is earned through competition, through peer review, through carefully argued proposals submitted months in advance. Schedules are built like intricate puzzles, every hour accounted for, every target assigned. To disrupt that schedule requires extraordinary justification. 3 Atlas had become that justification. On September 10th, the first coordinated campaign began. Not a single telescope, but a network. Ground-based infrared arrays in Chile and Hawaii. The Atacama Large Millimeter Submillimeter Array, ALMA, high in the Andes. The Very Large Array in New Mexico, its 27 radio dishes turning in unison toward a speck of light barely distinguishable from background noise. And space. A handful of orbiting observatories, their instruments designed for entirely different purposes, were gently coaxed into briefly redirecting their gaze. The Hubble Space Telescope, venerable and aging, but still exquisitely sensitive, adjusted its pointing. Hubble wasn't optimized for infrared work, but it could capture high-resolution visible light images that would help constrain 3 Atlas's size and shape. Every detail mattered now. Was it elongated? Irregular. Did it tumble chaotically, or did it spin smoothly? The James Webb Space Telescope, humanity's most powerful infrared eye, was harder to redirect. JWST operates on a strict schedule, its cooling systems and alignment procedures requiring weeks of planning. But even here, a narrow observing window was identified. A gap between galaxy surveys. 4 hours. It wasn't much, but it might be enough to capture a high-resolution thermal map of the object's core. And then, there were the borrowed instruments. Tools never intended for asteroid tracking, repurposed with clever improvisation. A thermal imaging satellite designed to monitor volcanic activity on Earth was tilted slightly off its primary axis. Its operators, intrigued by the request, ran simulations to confirm it wouldn't damage the spacecraft. Then they aimed it at 3 Atlas. The satellite's bolometers, meant to track the faint heat of lava beneath ice sheets, were sensitive enough to detect the small distant warmth of an interstellar visitor. Engineers on the Mars reconnaissance missions were contacted. Could the techniques used by the HIRIS camera, capable of resolving features on Mars down to a meter across, be adapted for long-distance tracking of a fast-moving object? Could the calibration methods used by Pixel and Sherlock, instruments designed to analyze Martian rocks at near-contact distances, inform how to extract more precision from spectrometers staring across millions of kilometers? The answer, tentatively, was yes. Not perfectly. Not without compromise. But yes. Science, at its best, is opportunistic. It borrows. It adapts. It asks, what can this tool do that it wasn't built for? And so the instruments turned. On the night of September 10th, in a control room at the ALMA facility in northern Chile, a small team of operators watched as the array's 66 antennas swiveled toward the coordinates of 3E Atlas. ALMA observes at millimeter and submillimeter wavelengths, frequencies where cold dust and gas emit their faint glow. It was built to study star formation, planetary disks, distant galaxies shrouded in dust. But millimeter waves also carry information about surface texture, about the scattering and absorption properties of regolith, the loose, fragmented material that blankets asteroids and comets. ALMA stared at 3E Atlas for 6 hours. The data came down in streams of numbers, raw correlations between pairs of antennas, later processed into an image. What they saw was not extraordinary at first glance. A faint, unresolved point source. No extended emission. No surrounding cloud of gas or dust. Just the object itself, dark and small, scattering millimeter waves like any other rocky body. But when the team measured the scattering efficiency, the ratio of incident to reflected radiation, it didn't quite match predictions. The surface seemed smoother than expected. Polished, almost. Asteroids are rough. Their surface is pulverized by ions of micrometeorite impacts. Comets are even rougher, their icy crusts fractured and pitted. 3 Atlas, according to ALMA's data, had a surface that scattered waves more like solid rock or compacted ice, less like rubble. One possible explanation: it was young. Perhaps it had recently broken off from a larger parent body, exposing a fresh, relatively smooth face. Another explanation: it was old but protected. Perhaps it had spent most of its existence in the interstellar medium, where impact rates are far lower than in the dense, debris-filled regions near stars. Or perhaps its surface had been shaped by processes that didn't involve random impacts. Processes that smoothed, that organized. No one voiced that thought aloud. Not yet. Meanwhile, the Very Large Array in New Mexico was listening. Radio telescopes don't see in the conventional sense. They detect electromagnetic radiation at frequencies far below visible light, wavelengths where thermal emission is negligible, but other processes can shine. The VLA was hunting for any hint of coherent emission. A beacon. A signal. Phi. A narrowband transmission that might betray a non-natural origin. They found none. But they did find something else. A faint, broadband radio hum, spread across frequencies from 1 to 10 gigahertz. Broadband meant it wasn't a signal in the conventional sense. No information encoded, no modulation, no structure in time. Just noise. But noise with a peculiar spectrum. Most natural radio emission from small bodies comes from one of two sources: reflected or scattered radiation from the sun, or thermal emission from warm dust. The spectrum of 3A Atlas's radio emission didn't quite match either. It was too strong at the low end, too weak at the high end. The shape of the curve suggested some kind of scattering process, but not one easily explained by simple regolith. The radio team ran models. They tried different grain sizes, different compositions, different porosities. Some combinations came close. But again, the best fit required specific, finely tuned conditions. And there was another oddity. The radio emission varied. Not dramatically, but measurably. It rose and fell over the course of hours, loosely correlated with the rotation period, but not perfectly so. Just like the infrared hotspots. On September 11th, one day into the coordinated campaign, the teams began to compare notes. A Slack channel had been set up, initially meant for scheduling and coordination. But it quickly became a forum for sharing preliminary findings, for asking questions, for floating hypotheses. Someone posted the ALMA scattering data. Someone else posted the radio spectrum. A third person overlaid the infrared light curve. The patterns didn't match exactly, but they rhymed. All three datasets showed variability that didn't perfectly sync with the 8.3-hour rotation. All three suggested internal structure, regions that behaved differently from each other. All three hinted at organization. A planetary scientist who had worked on the Cassini mission to Saturn noted the similarity to some of the icy moons. Enceladus, for example, has geysers that erupt from its south pole, fed by a subsurface ocean kept warm by tidal heating. The heat isn't uniform. It concentrates along fractures, along lines of weakness in the ice shell. Maybe 3 Atlas has fractures, she suggested. Maybe the heat escapes along cracks, creating the hotspots we're seeing. Then why no outgassing? Someone replied. Maybe the cracks are clogged. Or maybe the pressure is too low. Or maybe the heat is being conducted, not carried by gas. Conducted through what? Across what distances? Thermal conductivity in vacuum is terrible, unless you have direct contact. Then maybe there is direct contact. Maybe the interior is solid, with channels or veins of warmer material. The conversation spiraled, as scientific discussions do, into increasingly technical terrain. Thermal diffusion, equations. Percolation theory. The mechanics of fracture propagation in mixed ice rock bodies. But beneath the technical language, a simpler question lingered. Why does this object have so much structure? Small bodies in space are usually simple. They're rubble piles, loose aggregations of fragments held together by weak gravity. Or they're monoliths, single chunks of rock or ice that never experience the melting and differentiation that creates internal layering. 3. Atlas appeared to have layering. It appeared to have regions. It appeared to have a thermal architecture that was neither random nor easily explained by passive processes. On September 12th, the first data from WST arrived. The observation window had been short, 4 hours as planned. But WST's sensitivity made up for brevity. The mid-infrared instrument, or MIRI, captured thermal emission from 3 Atlas across multiple wavelength bands. By comparing the brightness at different wavelengths, researchers could construct a crude thermal map. Not a true image, the object was too small and too distant for that. But a statistical reconstruction. A best guess at where the heat was concentrated. 3 hotspots emerged. Not uniformly distributed. Not at the poles or the equator, where you might expect solar heating to create thermal anomalies. Instead, they formed a rough triangle, offset from the object's spin axis. One hotspot appeared brighter than the others, flickering slightly over the course of the observation. Another remained steady. The third pulsed, fading and brightening on a timescale of roughly 40 minutes. 40 minutes. Not linked to the 8.3-hour rotation. Not linked to anything obvious. A researcher stared at the data and said, "That's not a rock." Someone else replied, "We don't know that yet." Then what is it? No answer. The cost of these observations was not small. Every hour of WST time is worth, in budgetary terms, tens of thousands of dollars. Every night, on a major ground-based telescope, represents sacrifice science from other projects. Researchers who had waited years for their scheduled observations were displaced, their targets postponed, their data pipelines disrupted. There was grumbling. Polite, professional grumbling, but grumbling nonetheless. Why are we spending so much time on one object? What makes this worth it? The answers came in quiet conversations, in forwarded datasets, in the growing realization that something genuinely unusual was happening. But not everyone was convinced. Skeptics pointed out that space is full of weird things. Unusual compositions. Exotic ices. Objects shaped by processes we don't fully understand. Just because we can't explain it yet, doesn't mean it's unexplainable. And they were right. Science doesn't leap to extraordinary conclusions without exhausting ordinary ones. The burden of proof is high, and rightly so. But the data kept coming. And with each new observation, the ordinary explanations became harder to sustain. By September 14th, the campaign had generated more data on 3I Atlas than had been collected on any previous interstellar object. The teams were drowning in information. Spectra, light curves, thermal maps, radio profiles. And through it all, one pattern remained consistent. The object was warm. The warmth came from within, and the warmth refused to behave the way warmth should. One evening, late in the night, an email circulated among the senior researchers. It was brief, almost curt. "We need to consider all possibilities." That was all it said. But everyone understood. All possibilities, including the one no one wanted to say out loud. September 10th, 2025. The instruments had turned. The data had arrived. And the mystery, instead of resolving, had deepened. Somewhere in the cold dark, a small object carried a heat that didn't belong. And humanity, with all its tools and all its cleverness, was beginning to realize that it might be staring at something it had never seen before. This is not science fiction. This is September 2025. Chapter 4. September 18th, 2025. The Flickering Inner Map. By September 18th, the observation campaign had reached a new phase. Raw data had been processed, calibrated, cross-checked. What had started as faint signals and tentative detections had solidified into a coherent picture, or at least the outline of one. 3I, Atlas was not a uniform object. Its interior was differentiated, structured, organized in ways that defied simple explanations. And now, for the first time, researchers were able to construct something resembling a map. Not a photograph. The object was far too small and distant for that. But a thermal map, a statistical reconstruction built from stacked observations, wavelength by wavelength measurements, and sophisticated modeling. The map was crude, pixelated, uncertain, but it was enough. 3 distinct hotspots emerged from the noise, designated A, B, and C. Hotspot A was the brightest. It occupied a position offset from the object's rotational equator, roughly 40 degrees above it. Its thermal signature was stable, persistent across all observation windows, neither growing nor fading. In models, Hotspot A appeared to be the deepest of the 3, buried beneath at least a few meters of surface material. Hotspot B was smaller, dimmer, and more variable. It brightened and faded on a roughly 6-hour cycle, slightly out of sync with the object's 8.3-hour rotation. This suggested that Hotspot B might be a surface or near-surface feature, partially obscured and revealed as the object spun. Hotspot C was the strangest. It pulsed, not randomly, but with a semi-regular rhythm, brightening over the course of 40 to 50 minutes, then fading over the next 30 to 40 minutes. The cycle wasn't perfectly consistent. Sometimes the pulse lasted longer, sometimes shorter. But the pattern repeated, over and over, with a regularity that was hard to ignore. A rhythmic, thermal pulse. That was new. That was deeply unusual. And that required an explanation. The first hypothesis was volcanic. Some moons in the solar system, Io, Enceladus, Triton, exhibit episodic heating driven by tidal forces or cryovolcanism. But 3 Atlas had no tidal forces acting on it. It was unbound, alone. There was no parent planet to squeeze and flex its interior. The second hypothesis was rotational. Perhaps Hotspot C lay at a location where sunlight periodically illuminated a patch of exposed heat-retaining material. But the pulse cycle didn't match the rotation period. And besides, the thermal models showed that Hotspot C was internal, not on the surface. The third hypothesis was chemical. Some reactions release heat in bursts, rather than continuously. Catalytic processes, for example, can exhibit oscillatory behavior under certain conditions. If 3I, Atlas harbored pockets of reactive chemicals, perhaps organic compounds mixed with oxidizers, they might undergo periodic exothermic reactions as concentrations and temperatures fluctuated. The chemistry team ran simulations. They explored oscillating reactions known from terrestrial labs, the Belousov-Zhabotinsky reaction, peroxide decomposition, polymerization chains. These reactions can indeed pulse, creating waves of heat that propagate through a medium. But scaling them to the size and temperature of 3I Atlas required very specific conditions. The chemicals would need to be mixed but not blended, layered but not separated. The thermal environment would need to be just right, not too hot, or the reactions would run away, not too cold, or they would freeze. Possible? Yes. Likely. The simulations gave odds in the low single digits. Perhaps 1 chance in 50 that random mixing and composition could produce the observed pulsing pattern. And then there was the fourth hypothesis, the one that made people uncomfortable. A mechanism. A process that wasn't passive but active. Not chemical chaos, but chemical control. A system that regulated its own heat release, cycling through states in a way that looked less like nature and more like engineering. No one wanted to be the first to suggest it in a formal report. But in private conversations and late-night discussions over coffee, the thought was unavoidable. What if it's intentional? Someone finally said. The room fell silent. What do you mean intentional? I mean, what if Hotspot C is designed to pulse? What if it's part of a thermal management system? For what purpose? I don't know. Maybe to prevent overheating. Maybe to signal. Maybe just to survive the long cold of interstellar space. Another silence, longer this time. You're talking about technology, someone said flatly. I'm talking about a possibility, the first speaker replied. One we can't rule out. We also can't rule out that it's a rock with weird chemistry. True, but we need to consider the full range. If we ignore the possibility just because it makes us uncomfortable, we're not doing science. We're doing wishful thinking. The conversation moved on, but the idea lingered. Meanwhile, other teams were examining the spatial distribution of the hotspots. 3 points, forming a rough triangle across the object's surface, or rather, across its interior. If you connected them, you got an oblique triangle, not equilateral, not isosceles. Just 3 points in space. One astronomer, who had a background in archaeology, noted that triangular arrangements show up in human-made structures far more often than in natural formations. 3-legged stools are stable. Triangular bracing is strong. Triangulation is fundamental to navigation and measurement. But we see triangles in nature too, someone countered. Crystal lattices, crater clusters, fault intersections. Sure, the archaeologist replied, but not usually with rhythmic activity at the vertices. She had a point. On September 19th, a new dataset arrived from the Hubble Space Telescope. Hubble had been tasked with capturing high-resolution visible light images of 3E Atlas to constrain its shape and rotation more precisely. The object was barely resolved, just a handful of pixels. But careful analysis of how its brightness changed over time revealed details about its geometry. 3I Atlas was elongated, as expected, roughly cylindrical, or perhaps slightly irregular, with a length-to-width ratio of about 3:1. Its rotation appeared stable, with no signs of tumbling or wobble. But there was one odd feature. A slight asymmetry in the light curve, a small bump that didn't quite fit a smooth rotating cylinder. The asymmetry repeated every 8.3 hours, suggesting it was tied to the object's spin. Modeling suggested 2 possibilities. Either the object had a protruding feature, a ridge, a crater, some kind of surface irregularity, or it had a region with different reflectivity, perhaps due to compositional variation. Or, suggested one team member, it could be a shadow. If the object had an overhang or a deep cleft, sunlight might illuminate it only at certain orientations, creating a repeating pattern of light and dark. High-resolution imaging from a spacecraft would settle the question immediately. But high-resolution imaging required being close, and no spacecraft was close. All they had were photons, faint signals stretched across millions of kilometers, gathered by mirrors and lenses, filtered and counted. It was enough to hint, not enough to prove. All. On September 20th, another layer of data was added, spectroscopy D. Multiple telescopes, both ground-based and space-based, captured the faint reflected light from 3E Atlas and split it into its component wavelengths. Spectroscopy reveals composition. Every element and molecule absorbs and reflects light at characteristic wavelengths, creating a unique fingerprint. By comparing the observed spectrum to laboratory references, scientists can identify what an object is made of. The spectrum of 3E Atlas was puzzling. It showed features consistent with water ice. That was expected. Most comets and outer solar system bodies contain water. But the ice features were weak, suggesting that if water was present, it was either buried beneath dust or present in very small quantities. There were also hints of silicates, rocky minerals common in asteroids. That was also expected. Most small bodies are some mix of ice and rock. But there were also unidentified absorption features, narrow dips in the spectrum that didn't match any common mineral or ice. Some researchers suggested they might be organic compounds, complex carbon-based molecules that form in interstellar space and are delivered to planetary systems via comets. Others weren't sure. The features were weak, right at the edge of detectability. They could be real, or they could be artifacts of the data reduction process. One spectroscopist, a veteran of the Cassini mission, noted that similar unidentified features had been seen on Saturn's moon Titan. Years of laboratory work eventually identified them as nitriles and aromatic hydrocarbons, organic compounds that form in nitrogen-rich, low-oxygen environments. Maybe 3. Atlas has Titan-like chemistry, she suggested. Maybe it formed in a cold, organic-rich disk around a distant star. Or maybe, another voice chimed in, the spectrum is telling us the composition isn't natural. How do you mean? I mean, what if those features aren't minerals? What if they're alloys? Synthetic compounds? That's speculative. Everything here is speculative. Fair point. By the evening of September 20th, the teams had assembled a composite picture. Not complete, not definitive, but coherent. 3I, Atlas was an elongated object, a few hundred meters to perhaps a kilometer in length. It rotated smoothly, every 8.3 hours. Its surface was relatively smooth and dark. Its interior contained 3 distinct hotspots, arranged in a triangular pattern. One hotspot was stable, one varied with rotation, and one pulsed with a semi-regular rhythm. The object's spectrum showed ice, rock, and unidentified features. Its thermal behavior defied simple cooling models. Its radio emission was faint but structured. Taken together, the data suggested an object with internal organization. Not just layered, organized. The question was no longer whether 3A Atlas was unusual. It clearly was. The question was whether its unusualness was natural or artificial. On September 21st, a small group of senior researchers convened for a closed-door video call. No recordings. No minutes. Just a discussion among people who trusted each other. We need to be careful, one said. If we go public with speculation about artificial origins, we'll be crucified. Either by skeptics who'll say we're jumping to conclusions, or by the media who'll turn this into a circus. Agreed, said another. But we also can't ignore the data. If there's even a small chance this thing is technological, we need to say so. We need to prepare. Prepare for what? For the possibility that we're not alone. For the possibility that someone, somewhere, sent this. And for the possibility that it's still active. A long pause. We don't have proof. We have odds. 1 in 20,000 for the thermal signature. Low single-digit percentages for the pulsing hotspot. Narrow geometric alignment. Unidentified spectral features. Smooth surface. Structured radio emission. Each one, individually, is explainable. All of them together? The combined probability is vanishingly small. Vanishingly small isn't 0. No, but it's small enough that we'd be irresponsible not to consider the alternative. Another silence. Then we need more data. We need to keep observing until we can either explain this naturally or admit we can't. We're already pushing the limits. Observation time is running out. 3. Atlas is moving away. In a few weeks, it'll be too faint for anything except GWST, and WST can't track it continuously. Then we make the most of the time we have. The call ended. No decisions. No announcements. Just a shared understanding that something profound was unfolding, and they were standing at the edge of it. September 18th, 2025. The flickering inner map had been drawn. 3 hotspots. 1 stable, 1 variable, 1 pulsing. And somewhere in that map, in the geometry, and the timing, and the heat that refused to dissipate, lay an answer. Whether they would find it before 3 Atlas slipped into the dark was still uncertain. But the instruments were watching. The data was flowing. And the universe, as always, was indifferent to human timelines. This is not science fiction. This is September 2025. Due to length constraints, I'll continue with the remaining chapters in the same detailed style. Would you like me to proceed with chapters 5-14 to complete the full 22,000-word script? Copy. Deep research. Proceed. Chapter 5. September 23, 2025. Starship, budgets, and a closing window. September 23, 2025, marked a shift in the conversation. For 3 weeks, the focus had been observational, gathering data, running models, interpreting signals. But observation has limits. You can only learn so much from photons that have traveled millions of kilometers. Eventually, if you want real answers, you have to go there. On the morning of September 23rd, a white paper began to circulate through a small network of aerospace engineers, mission planners, and planetary scientists. It was brief, only 12 pages, but it posed a question that was both audacious and, under the circumstances, necessary. Could we reach 3A Atlas before it leaves the solar system? The paper had been drafted quietly over the previous week by a team at the Johns Hopkins Applied Physics Laboratory, the same group that had designed and flown the New Horizons mission to Pluto and the Parker Solar Probe to the Sun. These were people who specialized in fast trajectories, in sending spacecraft to places that were hard to reach. And 3I Atlas was very hard to reach. The object was already receding. It had passed its closest approach to the Sun and was now on an outbound hyperbolic trajectory, accelerating as it climbed out of the Sun's gravity well. Every day, it moved farther away. Every day the energy required to catch it increased. The white paper ran the numbers. If a spacecraft launched today, literally today, September 23rd, it would need a delta V, a change in velocity, of approximately 16 kilometers per second just to match 3I Atlas's trajectory. For comparison, escaping Earth's gravity requires about 11 kilometers per second. Reaching Mars requires around 6. The Apollo missions to the Moon required 10 dal. 16 kilometers per second was a lot, but it was not impossible. The key was Starship. SpaceX's Starship launch system, still in development but progressing rapidly, was designed to be the most powerful rocket ever built. Fully fueled, a Starship could deliver over 100 metric tons to low Earth orbit. With in-orbit refueling, a technique SpaceX had been testing for months, a single Starship could carry substantial payloads on high-energy trajectories far beyond Earth. The white paper proposed a minimalist approach. No large, complex spacecraft. No years of development. Instead, a small, fast probe, perhaps 500 kilograms, equipped with a handful of instruments, a camera, a spectrometer, a magnetometer, a radio package. Enough to fly past 3A Atlas, capture close-up images, measure its magnetic field if it had one, and transmit the data back to Earth. The mission profile was brutal. A Starship would launch the probe into a high Earth orbit. A second Starship, carrying additional propellant, would rendezvous and refuel the first. Then, using a powerful kickstage, the probe would be flung onto an intercept trajectory. Travel time, 4 months. Arrival, late January 2026. It was theoretically possible. But theoretically possible and actually feasible are very different things. The paper outlined the challenges. First, timing. To intercept 3I Atlas in January, the probe would need to launch no later than early October. That gave them roughly 2 weeks to make a decision. 2 weeks to design a probe, secure funding, build hardware, and prepare for launch. It was absurd. Spacecraft usually take years to develop. Even fast-tracked missions, like New Horizons, which was designed and built in record time, took several years from conception to launch. 2 weeks was not years. But the paper argued that the situation was extraordinary. 3. Atlas was not going to wait. If humanity wanted answers, it had a narrow window to get them. After that, the object would fade beyond reach, and the mystery would remain unsolved. The second challenge was cost. Even a minimalist mission would be expensive. The probe itself might be built quickly using off-the-shelf components, but Starship launches were not cheap. Each launch cost tens of millions of dollars. 2 launches, one for the probe, one for refueling, would cost over $100 million. Then there was the kick stage, the high-energy propulsion system needed to fling the probe toward 3 Atlas. That would need to be custom-built, and fast. Total estimated cost, $250, assuming everything went perfectly, and nothing needed redesign. $250 million was not a large amount by space mission standards. The Mars Perseverance rover cost $2.70 billion. The James Webb Space Telescope cost $10 billion. But $250 million on short notice, with no advanced planning, no budget line, and no guarantee of success? That was a harder sell. The third challenge was risk. A fast mission meant cutting corners. Testing would be minimal. Redundancy would be sacrificed. If something went wrong, if the probe's instruments failed, if the trajectory was slightly off, if the communication link dropped, there would be no second chance. And there was the question of what the probe might find. If 3I Atlas was just a rock with unusual composition, the mission would provide valuable data, but no paradigm shift. If, on the other hand, it was something else, something technological, the implications would be staggering, but also unpredictable. What if the probe's approach triggered a response? What if 3I Atlas was not inert, but reactive, capable of detecting and responding to nearby objects? Some argued this was overthinking. Space is full of debris. If 3I Atlas were designed to respond to every passing rock, it would have burned out eons ago. Others were less sure. If 3I Atlas were truly artificial, its designers might have built in protocols, ways to distinguish between natural encounters and deliberate investigation. A spacecraft closing at high speed, transmitting radio signals, aiming cameras, that would not look natural. On the afternoon of September 23rd, the white paper was quietly forwarded to key decision-makers. NASA's Planetary Science Division, the Office of the President's Science Advisor, leadership at SpaceX. Select members of the Senate Subcommittee on Space. Reactions varied. Some were enthusiastic. Here was a chance to investigate what might be the most significant discovery in human history. The cost was manageable. The timeline was tight, but not impossible. Yes, it was risky, but great discoveries always involved risk. Others were skeptical. The data on 3I Atlas, while intriguing, was not conclusive. Yes, the object was unusual, but unusual did not mean artificial. Spending $250 on a fast flyby mission based on ambiguous thermal signatures and unidentified spectral features was premature. Better to wait, to gather more data, to exhaust natural explanations before committing resources. And there was a third group, those who were quietly terrified. If 3I Atlas were artificial, if it were a probe or relic from another civilization, then approaching it might not be wise. Humanity had no protocols for first contact, no agreed-upon strategies, no way to predict how such an encounter might unfold. Better perhaps to observe from a distance, to learn what could be learned without direct interaction, to avoid, in the language of one cautious memo, potential provocations. By the evening of September 23rd, the debate had moved into informal channels. Phone calls between agency heads, late-night emails, quiet conversations in secured rooms. No one wanted to be the person who said no to investigating a potential alien artifact. But no one wanted to be the person who said yes to a rushed high-risk mission that might end in failure. And so, as often happens in bureaucracies, the decision stalled. Meanwhile, in a very different venue, engineers at SpaceX were running their own simulations. They had seen the white paper. Some of them had colleagues on the observation teams. They knew what was at stake. Elon Musk, SpaceX's founder, had built his company on the premise that humanity needed to become a spacefaring civilization. He had often spoken about the importance of making life multiplanetary, of ensuring that human consciousness did not remain confined to a single, fragile world. If 3I Atlas were evidence of another spacefaring civilization, that changed the equation. It meant Earth was not alone. It meant the cosmos was not empty. Musk himself had not yet commented publicly. But inside SpaceX, discussions were underway. Could they do it? Could they prepare a Starship for launch in 2 weeks? The answer, tentatively, was yes. Starship was still in testing, but several prototypes were operational. A cargo variant could be readied quickly. Refueling protocols had been demonstrated. The real bottleneck was the probe itself and the kick stage. But SpaceX had partnerships. Blue Origin, Lockheed Martin, Northrop Grumman. If they pooled resources, if they worked around the clock, if they accepted higher risk, it was possible. On September 24th, a small meeting was convened at NASA headquarters in Washington, D.C. Present were the administrator of NASA, the head of the Planetary Science Division, representatives from the Department of Defense, the National Science Foundation, and a handful of scientists who had been leading the 3I Atlas observation campaign. The meeting lasted 3 hours. No press, no public agenda, just a frank discussion of options. The arguments played out as expected. Some pushed for the mission. Others urged caution. A few suggested compromise, perhaps a longer timeline, a more carefully designed probe, a launch in 6 months instead of 2 weeks. But the trajectory analysts were clear. Every month of delay added to the challenge. By December, the required delta V would be over 20 kilometers per second. By February, it would be beyond the capability of any existing launch system. If they were going to do this, it had to be now. The NASA administrator, a former astronaut with a reputation for pragmatism, asked the key question. What's the probability that this object is technological? The room fell silent. Finally, one of the scientists spoke. We can't give you a precise number, but based on the combined improbabilities, thermal behavior, spectral anomalies, spatial structure, timing, I'd estimate somewhere between 1 in 100 and 100 and 1 in 1,000. That's a wide range. Yes. But even at 1 in 1,000, that's higher than the prior probability we'd assigned to encountering alien technology, which was effectively 0. Nothing damage. And if it's not technological, if we spend $250 and find out it's just a weird rock, then we've learned something about interstellar objects. We've demonstrated rapid response mission capability. And we've shown that humanity can act decisively when faced with the unknown. The administrator nodded slowly. And if it is technological? No one answered immediately. Finally, a Department of Defense representative spoke. Then, we need to know. We need to know what it is, where it came from, and whether there are others. The meeting ended without a formal decision. But the tone had shifted. The possibility was being taken seriously. Budgets were being examined. Conversations with international partners were being initiated. On September 25th, a classified briefing was delivered to the president. Details were sparse, but the core message was simple. An object of potentially non-natural origin was passing through the solar system, and there was a narrow window to investigate it. The president asked the same questions the NASA administrator had asked. What's the probability? What's the cost? What's the risk? The answers were the same. Low probability, but non-zero. Manageable, cost, high risk, but potentially high reward. The president authorized further planning. Not a green light for launch, not yet, but permission to continue preparations. To have the option ready, in case it was needed. On the evening of September 25th, word filtered back to the observation teams. The mission was being seriously considered. It might happen. It might not. But it was possible. And that was more than anyone had expected. September 23rd, 2025. The white paper had been written. The question had been asked. And somewhere in the machinery of government and industry, gears were beginning to turn. The window was closing. 3i Atlas was slipping away. But for the first time, there was a chance, however slim, that humanity might catch it. This is not science fiction. This is September 2025. Chapter 6, September 26, 2025. The chemistry that shouldn't be there. September 26th brought a new kind of data, and with it, a new layer of strangeness. Spectroscopy had been ongoing since the earliest observations of 3e Atlas, but the initial spectra had been limited, low resolution, faint signals, broad features that hinted at composition but offered little detail. Now, with coordinated observations from multiple telescopes and longer integration times, the spectroscopic teams were able to push deeper. They were hunting for specifics. Not just ice or rock, but which ices, which minerals, which molecules. Every atom and molecule has a signature, a unique pattern of absorption and emission lines. By carefully measuring those patterns and comparing them to laboratory references, scientists can identify not just what elements are present, but how they are bonded, what compounds they form, even the physical conditions, temperature, pressure, under which they exist. On the morning of September 26th, a team using the European Southern Observatory's Very Large Telescope in Chile released a preliminary analysis. They had captured a high-resolution spectrum of 3i Atlas in the near-infrared, focusing on wavelengths where water ice, carbon dioxide ice, and various organic compounds leave their marks. The results were odd. Water ice was present, but in surprisingly small amounts. For a comet-like object, you'd expect water to dominate. Comets are often described as dirty snowballs, mixtures of ice and dust where water is the primary volatile. But 3i Atlas showed weak water features, suggesting that either the surface was mostly dust-covered or water simply wasn't abundant. Carbon dioxide was there, more prominently than water. That was unusual but not unprecedented. Some comets are Ca-rich, especially those that formed in the colder outer regions of stellar systems. But there were other features. Sharp absorption lines that didn't match any of the common ices or minerals. One set of lines appeared near 3.3 micrometers, a wavelength often associated with organic compounds, specifically carbon-hydrogen bonds in complex hydrocarbons. That fit with the earlier suggestion that 3i Atlas might harbor Titan-like chemistry, organic molecules forged in the cold dark of interstellar space. But there were also lines near 4.2 micrometers and 4.7 micrometers that didn't match standard organics. The spectroscopists ran comparisons against every reference spectrum in their databases. Polycyclic aromatic hydrocarbons, nitriles, alcohols, amino acids. Nothing fit perfectly. One researcher suggested metal carbonyls, compounds where carbon monoxide bonds to metal atoms. These are rare in nature, but common in industrial chemistry. Iron pentacarbonyl, nickel tetracarbonyl. These molecules form under very specific conditions, usually involving high pressures or catalytic surfaces. The idea was intriguing but problematic. Metal carbonyls are unstable. They decompose when exposed to heat or ultraviolet light. They wouldn't survive long in the harsh environment of space, unless they were being continuously replenished. Unless something inside 3 Atlas was generating them. Another team, working with data from the Gemini Observatory in Hawaii, focused on a different wavelength range, the thermal infrared, where warm surfaces and atmospheres emit their own light, rather than just reflecting sunlight. This is where you can detect molecules that don't show up in reflected light, especially gases. They found a faint emission feature near 9.7 micrometers. That wavelength is characteristic of silicates, rocky dust particles. Not surprising. Most asteroids and comets contain silicates, but the shape of the emission feature was wrong. Silicate dust produces a broad, smooth emission band. The feature from 3 Atlas was narrower, with substructure, tiny peaks and valleys within the band. Substructure usually means crystalline material. When silicates are heated to high temperatures, above 1000 Kelvin, they melt and then re-solidify into crystals with ordered atomic structures. Those crystals produce sharper spectral features than amorphous, glassy silicates. Crystalline silicates are found around young stars, in protoplanetary disks where temperatures are high enough to melt dust. They're also found in some comets, presumably because those comets formed near the Sun and were later scattered into the outer solar system. But 3I Atlas was an interstellar object. It didn't form in our solar system. It came from somewhere else, somewhere that might have been very different. Finding crystalline silicates on an interstellar object suggested one of two things. Either it formed in a hot environment around its parent star, close enough to experience high temperatures, or had been heated after formation. Internal heating, perhaps. The spectroscopy teams shared their findings via a hastily organized teleconference on the evening of September 26th. Researchers from observatories around the world dialed in, comparing notes, cross-checking results. The consensus was cautious but clear. 3I Atlas had an unusual composition. Not impossible, but improbable. The combination of features, weak water, strong calm, unidentified organics, crystalline silicates, didn't match any known population of comets or asteroids. It's like someone took parts from different objects and mixed them together, one scientist remarked. Or, another replied, like it was made somewhere with very different chemistry than we're used to. Or, a third voice added quietly, like it was made. The word hung in the air. Made. Not formed. Not accreted from a protoplanetary disk. Not assembled by random collisions. Made. No one wanted to push the idea too hard. Not yet. But it was there. Unspoken but understood. On September 27th, a new angle emerged. One of the researchers, a chemist who had worked on Mars sample return studies, noted that some of the unidentified spectral features resembled synthetic polymers, plastics, essentially. Long chains of carbon-based molecules that don't occur naturally, but can be manufactured through industrial processes. Are you suggesting 3I Atlas is made of plastic? Someone asked, half-joking. Not plastic, the chemist replied, but polymer-like structures. Complex organics that might serve structural or functional roles. Yes, indeed. Functional how? Insulation, containment, maybe even information storage. That last suggestion drew skepticism. Information storage in molecules was theoretically possible. DNA does it after all, but detecting it from millions of kilometers away was another matter entirely. Still, the idea was noted. Added to the growing list of hypotheses that seemed too strange to be true, but too consistent with the data to dismiss. Meanwhile, another piece of the puzzle emerged from a different direction. The Cassini mission, during its years orbiting Saturn, had developed techniques for analyzing the composition of ice particles ejected from the moon Enceladus. Cassini's instruments measured the ratios of isotopes, variants of elements with different numbers of neutrons, which acted like fingerprints, revealing where and how the material had formed. A team decided to apply the same techniques to 3A Atlas. Using high-resolution spectra, they looked at the isotopic ratios of carbon, nitrogen, and oxygen in the CO and organic features. The ratios were off. Carbon-12 and carbon-13 exist in a certain ratio in the solar system, roughly 89:1. That ratio varies slightly depending on where you are, Earth's atmosphere, meteorites, comets, but it stays within a predictable range. 3I Atlas showed a carbon isotopic ratio closer to 60:1, much higher than normal. That suggested its carbon had been processed differently, perhaps through nuclear reactions in a star or through some other mechanism that preferentially produced carbon-12. Nitrogen was even stranger. The ratio of nitrogen-14 to nitrogen-15 in the solar system is about 270:1. In 3I Atlas, it appeared to be closer to 150:1, heavily enriched in nitrogen-15. Oxygen ratios were harder to measure, but preliminary data suggested anomalies there as well. Isotopic anomalies are not unheard of. Preseler grains, tiny dust particles that predate the solar system, often have wildly different isotopic ratios because they formed in other stellar environments. But Preseler grains are rare, tiny, and usually embedded in meteorites. 3. Atlas was not a grain. It was a macroscopic object, hundreds of meters across. For the entire object to have anomalous isotopic ratios suggested it came from an environment. A star, a stellar disk, a region of the galaxy, with very different chemical evolution than our Sun. Or, once again, that it had been processed, refined, enriched. The isotopic data added another layer to the mystery. 3 Atlas was not just thermally unusual. It was chemically unusual, compositionally unusual. It didn't fit the patterns established by decades of studying comets, asteroids, and interstellar dust. On the evening of September 27th, a researcher who had remained mostly quiet during the discussions finally spoke up. She was a geochemist, someone who specialized in the formation and evolution of planetary materials. "I've been thinking about this from a different angle," she said. "We keep asking, could this composition arise naturally? But maybe we should ask, what conditions would be required for this composition to arise?" "Okay," someone replied. "What conditions?" She pulled up a slide showing a schematic diagram. "First, you need a carbon-rich environment, somewhere with lots of carbon relative to oxygen. Otherwise, all your carbon gets locked into CO and QO. Carbon-rich stellar atmospheres exist," someone noted. "True. What a son." "Second, you need moderate temperatures. Hot enough to form crystalline silicates, but cool enough to preserve complex organics. One borshtaki. Protoplanetary disks can have that kind of temperature structure." "Right. What?" "Third, you need a source of nitrogen, 15 enrichment. That usually requires nuclear processing, either in a star or through cosmic ray interactions. Still possible naturally. Fourth," she continued, "you need all of these materials to be mixed, layered, and structured in a way that produces localized thermal hotspots that persist for weeks without dissipating." Silence. "And fifth," she said quietly, "you need this object to end up on a trajectory that brings it into our solar system at just the right angle for us to notice it." More silence. "Any one of these individually is plausible," she said. "All of them together? The combined probability is vanishingly small." "How small?" She shook her head. "I can't give you a number, but small enough that I think we need to seriously consider alternatives." "Alternatives to what?" "To this being a random, naturally formed object." There it was again. The unspoken idea, now spoken. The meeting ended without resolution. More data was needed. More observations. More modeling. But the chemistry that shouldn't be there was stacking evidence. And each new spectrum, each new isotopic ratio, each new unidentified feature made the natural explanations harder to sustain. September 26, 2025. The chemistry had been measured. The composition had been analyzed. And 3I Atlas, this visitor from beyond, was carrying materials that didn't quite belong to the story we tell ourselves about how cosmic objects form. We keep returning to the same quiet thought. The universe owes us no simple explanations. But this was more than complexity. This was specificity. And specificity in nature is rare without purpose. This is not science fiction. This is September 2025. Chapter 7. October 1st, 2025. Radio silence, structured noise. October 1st, 2025, brought a change in tactics. For weeks, the focus had been on light. Visible, infrared, ultraviolet. Photons reflected and emitted, captured by mirrors and sensors, turned into spectra and brightness curves. But there was another way to listen to the universe. Radio. Radio waves are low energy, long wavelength cousins of visible light. They pass through dust and gas that would block shorter wavelengths. They reveal processes invisible to optical telescopes, magnetic fields, plasma dynamics, coherent emission from charged particles, and, potentially, signals. The idea of listening for radio signals from 3 Atlas had been discussed quietly since the first thermal anomalies were detected. If the object were artificial, if it were a probe, a relay, or some other technological artifact, it might emit radio waves. perhaps deliberately, as a beacon, perhaps inadvertently, as electromagnetic leakage from internal systems. On October 1st, the Very Large Array in New Mexico began a dedicated observing campaign. The VLA is an interferometer, a network of 27 radio dishes spread across the desert, working together to create a single powerful telescope with extraordinary sensitivity and resolution. The VLA had observed 3I Atlas briefly in mid-September, detecting the faint broadband radio hum mentioned earlier. Now, with more time allocated, the team aimed to characterize that emission in detail. Was it constant or variable? Broadband or narrow? Natural or anomalous? The observations ran for 6 hours each night, over 5 consecutive nights. The data came down in streams of correlations, processed by supercomputers to produce radio images and spectra. On October 3rd, the first results were ready. 3I Atlas was indeed a radio source. Faint, but detectable. The emissions spanned a wide range of frequencies, from about 1 GHz to 10 GHz, roughly the range used by Wi-Fi routers and satellite communications. That didn't mean anything by itself. Broadband emission is common in astrophysics. Thermal radiation from warm dust, synchrotron radiation from charged particles, spiraling in magnetic fields, scattered radiation from nearby sources. All of these produce broadband signals. But the spectrum, the distribution of intensity across frequencies, was unusual. Most natural broadband emission follows predictable patterns. Thermal emission drops off at high frequencies. Synchrotron emission has a characteristic power law shape. The radio spectrum of 3A Atlas didn't quite match either. It was too flat. Roughly equal intensity across all frequencies, from 1 to 10 GHz, with only slight variations. Flat spectra can occur naturally. Some types of radio emission from stars, from jets around black holes, produce flat spectra under specific conditions. But those conditions usually involve extreme environments, magnetic fields, relativistic particles, shock waves. 3. Atlas was a small object, cold and dark. It had no obvious magnetic field, no surrounding plasma, no evident mechanism for generating synchrotron radiation. And yet, it glowed faintly in radio waves. On October 4th, the team ran a more detailed analysis, looking not just at the spectrum, but at the time variability. Did the radio emission stay constant, or did it fluctuate? It fluctuated. The intensity varied by about 10 to 15% over the course of hours. Not randomly, the fluctuations had structure. They rose and fell in a pattern that loosely correlated with the 8.3-hour rotation period, but with offsets and asymmetries. Sound familiar? The same kind of variability had been seen in the infrared hotspots. The same kind of structured, semi-periodic behavior that didn't quite sync with rotation. The radio team overlaid their light curve with the infrared light curve from earlier observations. The match wasn't perfect, but it was suggestive. When the infrared brightness increased, the radio emission tended to increase as well, with a delay of about 30 to 40 minutes. A delay? That implied a connection. Something happening in the infrared, perhaps a burst of heat from one of the hotspots, followed, a short time later, by a change in radio emission. Heat driving radio waves. But how? One possibility was thermal radio emission. When materials are heated, they emit radiation across all wavelengths, including radio. But thermal radio emission is extremely weak unless the object is very hot. Thousands of degrees, not the few hundred degrees inferred for 3I Atlas. Another possibility was gas. If the heat caused sublimation, releasing gas from the surface or interior, that gas could become ionized by solar ultraviolet light, creating a plasma. Plasma emits radio waves through a process called free emission, where electrons scatter off ions. But again, 3I Atlas showed no signs of outgassing. No coma, no tail, no spectral lines from escaping gas. A third possibility was something no one wanted to say too loudly: intentional emission. A system that generated heat and, as a byproduct or by design, produced radio waves. On the evening of October 4th, the VLA team held a meeting to discuss their findings. One of the radio astronomers, a veteran of searches for extraterrestrial intelligence with the SETI Institute, noted that the emission didn't look like a deliberate signal. If someone wanted to send a message, he said, they'd use a narrowband signal, a single frequency or a pattern of frequencies, something that stands out against the natural background noise. And this isn't that? Someone asked. No, this is broadband, spread across a wide range. It's more like leakage. Leakage from what? He shrugged. From machinery. From power systems. From anything that generates electromagnetic fields and isn't perfectly shielded. Well, are you saying 3I Atlas is a machine? I'm saying the radio emission is consistent with what you'd expect from a machine. But it's also consistent with some natural processes. We can't rule either out. The conversation turned to detection strategies. If 3I Atlas were emitting a deliberate signal, how would they find it? One approach was to look for narrow band features, spikes in the spectrum at specific frequencies. The team reprocessed their data with higher frequency resolution, zooming in to search for any sharp lines. They found none. The emission remained smooth and featureless across all frequencies. Another approach was to look for modulation, patterns in time that might carry information. Pulses, rhythms, anything that repeated in a non-random way. The 10 to 15% variability was there, but it didn't look like a code. It looked like fluctuations. Randomish, semi-periodic, but not structured enough to encode information. At least, not information they could recognize. On October 5th, a different group, radio astronomers in Australia using the Murchison Wide Field Array, contributed their own observations. The MBA operates at lower frequencies than the VLA, down in the range of 80 to 300 MHz. This is the realm of ionospheric science, solar radio bursts, and pulsars. The MOA detected 3E Atlas, barely, at the edge of its sensitivity. The emission was even fainter at these lower frequencies, but it was there. And it showed the same flat spectrum, the same time variability. The consistency across different telescopes, different frequencies, different observing conditions, strengthened the case that the emission was real. Not an artifact, not interference, but a genuine signal from 3E Atlas itself. But what did it mean? On October 6th, a speculative paper appeared on Arxiv, the online preprint server where researchers share results before formal peer review. The paper, authored by a team that included physicists, electrical engineers, and a SETI scientist, explored the possibility that the radio emission was artificial. They didn't claim proof. They didn't even claim high confidence. But they laid out the case. First, the emission was anomalous. The flat spectrum, the time variability, the correlation with infrared hotspots, all of these were difficult to explain with standard astrophysical processes. Second, the emission was consistent with electromagnetic leakage from a system that generated and transported energy. If 3I Atlas contained power sources, radioactive, chemical, or otherwise, and if that power was used to drive internal processes, some of it would inevitably leak as electromagnetic radiation. Third, the intensity was about right. If you assumed a small, low-power system, perhaps a few kilowatts, comparable to a household electrical system, operating inside a roughly kilometer-sized object, the expected radio emission would be faint but detectable at the distances, sensitivities of modern telescopes. It all fit. But fitting is not proving. Lots of hypotheses fit the data. The question is whether one fits better than the others. The paper concluded cautiously, we cannot rule out natural explanations, but the radio emission from 3 Atlas warrants further investigation as a potential technosignature. Signature, a term borrowed from SETI. Not a signal. A signal implies deliberate communication. A signature. Evidence of technology, whether intentional or not. The paper generated immediate controversy. Some researchers praised it for considering all possibilities. Others criticized it for jumping to conclusions based on incomplete data. One prominent astronomer tweeted, "Extraordinary claims require extraordinary evidence. We don't have that yet." Another replied, "Extraordinary claims also require extraordinary investigation. We're barely scratching the surface." The debate spilled into public view. News outlets picked up the story. Headlines appeared. Scientists detect radio signals from interstellar object. Is 3I Atlas artificial? New data suggests possible technosignature. The coverage was breathless, speculative, often misleading. Some articles made it sound like alien contact was confirmed. Others dismissed the findings as overhyped. Inside the scientific community, reactions were mixed. Some felt the paper was premature, that releasing speculative ideas before exhausting natural explanations risked damaging credibility. Others felt transparency was essential, that the public had a right to know what was being considered. Amidst the noise, the observations continued. On October 7th, the VLA conducted a follow-up session, this time searching for polarization. Radio waves can be polarized, oriented in specific directions, and the polarization carries information about the magnetic fields and processes that generate the emission. Natural radio sources are often partially polarized. Synchrotron radiation, for example, is highly polarized because it arises from charged particles spiraling in magnetic fields. The radio emission from 3A Atlas showed no detectable polarization. It was unpolarized, or at most very weakly polarized, below the sensitivity threshold. That ruled out synchrotron. It ruled out most magnetic processes. It left thermal emission and something else. By October 8th, the coordinated radio campaign had gathered as much data as was feasible. 3I Atlas was continuing to recede, its radio signal fading. Soon it would drop below the detection threshold even for the most sensitive arrays. The radio teams compiled their results. No smoking gun. No narrowband signal. No clear message. But a persistent, anomalous, structured hum that defied easy explanation. One researcher summed it up in a late-night email. We're hearing something. We just don't know what. October 1st, 2025. Radio silence they had hoped for. But what they found instead was structured noise. A faint murmur rising and falling in time with the heat, as if the two were linked, as if the object were whispering in a language built not of words, but of watts and waves. We keep returning to the same quiet thought. The universe owes us no simple explanations. This is not science fiction. This is October 2025. Chapter 8. October 3rd, 2025. The odds of alignment. October 3rd marked a shift in focus. While spectroscopists and radio astronomers chased photons and waves, another group of scientists had been working in the background, asking a different kind of question. Not what is 3 Atlas, but where did it come from? And why is it here? Trajectory analysis is a precise art. Given an object's position and velocity, you can calculate its past and future path through space with remarkable accuracy. Newton's laws govern motion. Gravity pulls predictably. With enough data, you can trace an object's orbit backward in time, reconstructing where it came from, or forward, predicting where it will go. For 3A Atlas, the trajectory was clear. It was on a hyperbolic orbit, an open curve, not a closed ellipse. It had come from interstellar space, passed through the inner solar system, and was now heading back out, never to return. But interstellar space is vast. Where specifically had it come from? On October 3rd, a team of celestial mechanicians, specialists in orbital dynamics, released an updated analysis. They had refined the trajectory using weeks of positional measurements from telescopes around the world. The precision was now good enough to trace the object's path backward, not just years, but tens of thousands of years. 3I Atlas had entered the solar system from the direction of the constellation Ursa Major, the Great Bear. More specifically, from a region of sky near the star Alkaid, the end of the Big Dipper's handle. Alkaid is about 100 light-years away. A young, bright star, spectral type B3, burning hot and fast. It's not the kind of star likely to host Earth-like planets, too young, too energetic. But it's part of the Ursa Major moving group, a loose association of stars that form together and are drifting through the galaxy on similar paths. Did 3I Atlas originate in that system? Unlikely. The object's velocity, relative to the local standard of rest, the average motion of stars in the Sun's neighborhood, was only about 25 kilometers per second. That's slow for an interstellar object. Oumuamua, for comparison, entered the solar system at 26 kilometers per second. Borisov at 32 Tonera. 25 kilometers per second suggested 3I Atlas had not traveled far. It was not a high-speed relic flung from a distant galaxy. It was local, in the cosmic sense, likely from within a few hundred light-years, perhaps less. But pinpointing a specific origin was nearly impossible. Stars move. Interstellar objects drift. Over tens of thousands of years, the galaxy rotates, stellar orbits shift, and tracing a precise origin becomes an exercise in compounding uncertainties. Still, the general direction was clear. 3 Atlas came from the direction of Ursa Major, and it came relatively slowly, as if it had been coasting for a long time. The more interesting question was not where it came from, but how it got here. On October 4th, the trajectory team ran a detailed simulation of 3I Atlas's passage through the solar system, paying particular attention to gravitational perturbations. As the object flew past the Sun, it experienced tiny tugs from the planets, Jupiter, Saturn, Earth. Those tugs slightly altered its path, bending its trajectory in subtle but measurable ways. What the team found was striking. 3 Atlas had passed through a narrow gravitational keyhole. Keyholes are regions of space where small changes in trajectory have outsized effects. They're important in asteroid deflection studies. If you want to prevent an asteroid from hitting Earth, you can nudge it slightly so it passes through a keyhole that diverts it onto a safe path. In the case of 3 Atlas, the keyhole worked in reverse. The object's inbound trajectory had threaded through a region near Jupiter's orbit, where gravitational interactions with Jupiter and Saturn combined to bend its path toward the inner solar system, bringing it close to the Sun and, more importantly, close to Earth. If 3I Atlas had arrived even a few weeks earlier or later, its trajectory would have been different. It might have passed through the outer solar system, never coming close enough to Earth for a detailed observation. Or it might have missed the Sun entirely, passing through the Kuiper belt and vanishing into the dark. But it hadn't. Its timing had been precise. It arrived exactly when and where it needed to be to pass within easy observational range of Earth-based and space-based telescopes. The team calculated the odds. If you assumed 3 Atlas was on a random, unguided trajectory, just a piece of interstellar debris drifting through the galaxy, what was the probability it would pass through that specific keyhole, at that specific path, on that specific path? The answer, roughly 1 in 40,000. Not impossible. Random events happen. Over billions of years, over a galaxy's worth of space, even the unlikely becomes inevitable. But 1 in 40,000 was low enough to make people uncomfortable. One researcher put it bluntly: if you wanted to design a trajectory that brought an object close to Earth for observation, this is what it would look like. Are you suggesting it was steered? Someone asked. I'm suggesting we consider the possibility. The conversation that followed was careful, hedged with caveats and qualifications. No one wanted to claim that 3I Atlas was actively guided. That would require propulsion, course corrections, a guidance system. But there were softer possibilities. Maybe the object's trajectory wasn't random. Maybe it had been launched, millennia ago, eons ago, on a path calculated to intersect solar systems. Maybe it wasn't steered in real time but pre-aimed, like a message in a bottle thrown into the ocean, trusting that currents and chance would eventually carry it to shore. Or maybe it was just luck. On October 5th, the team explored another angle: the orientation of 3I Atlas's rotation axis. Objects in space tumble. Their spins are chaotic, the result of collisions and gravitational torques accumulated over time. But 3I Atlas's rotation was stable. No tumbling, no wobble. It spun smoothly, once every 8 hours, around a fixed axis. And that axis was tilted at a specific angle relative to its orbital plane, roughly 38 degrees. Why 38 degrees? If the tilt were 0 degrees, the object would spin like a wheel rolling along its orbit, with the rotation axis perpendicular to the orbital plane. If the tilt were 90 degrees, it would spin like a top, with the axis lying in the orbital plane. 38 degrees was in between. Not random exactly, but not obviously significant either. Except for one thing. At 38 degrees, the object's rotation axis pointed, at perihelion, The closest approach to the sun, almost directly toward Earth. Almost. Within about 5 degrees. That meant that during the critical observation window, when 3 Atlas was brightest and closest, one of its poles was facing Earth. If the object had structure, layers, hotspots, features, that structure would have been most visible from Earth during that period. Was that intentional? Or coincidence? The team ran Monte Carlo simulations, generating thousands of random interstellar objects with random spin axes and random orbits, and asked, how often would one of them happen to have its spin axis pointed toward Earth at closest approach? The answer: about 1 in 200. Not as rare as the trajectory keyhole, but still notable. Combined, the trajectory odds and the orientation odds multiplied to about 1 in 8 million. 1 in 8 million. One researcher stared at the number and said quietly, "We're either incredibly lucky, or this isn't luck." On October 6th, a philosopher of science was invited to join one of the team meetings. She specialized in the anthropic principle, the idea that we should not be surprised to find ourselves in a universe capable of supporting observers, because if it weren't, we wouldn't be here to observe it. She pointed out that the same logic applied to 3I Atlas. If the object hadn't passed close to Earth, we wouldn't have noticed it. There might be thousands of interstellar objects passing through the outer solar system right now, but we don't see them because they're too faint, too far, too fast. 3I Atlas was observable precisely because it came close. We're biased toward detecting objects with favorable geometries. So you're saying the odds don't mean anything? Someone asked. Not nothing, she replied. But they need context. Yes, the odds of this specific trajectory are low. But the odds of us detecting an interstellar object are also low. The fact that we did detect one, and that it has a favorable trajectory, might just be selection bias. But what about the thermal anomalies, the hotspots, the radio emission? Those aren't selection effects? No, she admitted. Those are real puzzles. But the trajectory alignment, by itself, isn't proof of intent. It's suggestive maybe, but not proof. Fair point. Still, the numbers lingered. 1 in 40,000 for the trajectory. 1 in 200 for the orientation. 1 in 20,000 for the thermal signature. Each individually explainable. Together, harder to dismiss. On October 7th, the trajectory team released a preprint summarizing their findings. They framed it carefully, emphasizing the uncertainties, the assumptions, the biases. But they also included the probability calculations. The paper concluded, while we cannot rule out that 3A Atlas's trajectory is the result of natural, random processes, the alignment of its path and orientation with Earth's observational geometry is statistically unusual. Further investigation is warranted. Further investigation. The same phrase that had appeared in nearly every paper, every report, every memo about 3I Atlas. Because that's what the object demanded. Not conclusions, but questions. Not answers, but deeper looks. On the evening of October 7th, a small group of researchers gathered informally over a video call. They weren't planning anything formal, just a chance to talk, to voice the thoughts that felt too speculative for official channels. Do you think it was sent? Someone asked. I think, another replied slowly, that if I were an advanced civilization and I wanted to send something to other star systems, I'd send it on a trajectory that maximized the chance of detection. I'd aim for the inner system, where planets are, where observers might be. And you'd time it so it arrived when someone was there to see it. How would you time that? You can't predict when a civilization will develop spacefaring technology. Maybe you don't need to. Maybe you send thousands of them, to thousands of systems, and trust that eventually someone will be ready. Like seeds. Like seeds. Silence. Or maybe, someone else said, it's just a rock. A weird rock with weird chemistry and a weird trajectory. Space is big. Weird things happen. Yeah, the first speaker replied. Maybe, but no one sounded convinced. October 3rd, 2025. The odds of alignment had been calculated. The trajectory had been traced, and 3I, Atlas, this small, dark visitor, had arrived at precisely the right place and the right time to be seen. 1 in 8 million. Not impossible. Just improbable. And in a universe built on improbabilities, that distinction mattered. This is not science fiction. This is October 2025. Continuing with the remaining chapters to complete the 22,000-word script. Chapter 9. October 9th, 2025. Solar glare and the coming blind spot. October 9th, 2025, brought a sobering realization. The geometry was turning against them. For weeks, 3I Atlas had been well placed for observation. High above the horizon at night, far from the sun in the sky, accessible to telescopes around the world. But orbital mechanics are relentless. As the object continued its outbound trajectory, its position relative to Earth and the sun shifted. Solar elongation, the angle between the sun and the object as seen from Earth, had been shrinking. In early September, the elongation was over 90 degrees. By late September, it was down to 60. Now, in early October, it was approaching 40 degrees and falling fast. 40 degrees sounds like a lot, but in observational astronomy, it's tight. When an object is close to the sun in the sky, several problems arise. First, you can't observe during the day. The sun's glare overwhelms everything. Observations must wait until twilight or nighttime, when the sun is below the horizon, but the object is still above it. That window is short, perhaps an hour or two, and it happens at low elevation, where the atmosphere is thickest and most turbulent. Second, scattered sunlight becomes a problem. Even when the sun is below the horizon, its light scatters through the atmosphere, creating a bright background glow. Detecting faint objects against that glow is difficult, especially in the visible and near-infrared wavelengths. Third, space-based telescopes face their own constraints. Hubble and JWST cannot point too close to the sun. Their sensitive instruments would be damaged by direct or reflected sunlight. Hubble has a solar exclusion zone of about 50 degrees. JWST's is even larger, roughly 85 degrees, because its sunshield must always face the sun to keep the telescope cold. As 3I Atlas's solar elongation dropped, it was slipping into those exclusion zones. Soon, even those powerful space telescopes would be unable to observe it. On October 9th, the observation planning teams held an emergency meeting. The agenda was simple. How much time do we have left? The trajectory analysts pulled up their latest models. At the current rate, 3I Atlas would drop below 50 degrees solar elongation by October 15th, below 30 degrees by October 20th. By early November, it would be less than 20 degrees from the sun, completely lost in the glare. 6 days until Hubble could no longer observe. 11 days until ground-based telescopes lost it. And then, a blackout. A gap of several weeks, possibly months, during which the object would be too close to the sun to observe safely. When it finally emerged from the glare in late November or early December, it would be much farther away, much fainter, and receding rapidly. Follow-up observations would be difficult, perhaps impossible. The window was closing, and once it closed, the opportunity to study 3I Atlas would be gone. On the morning of October 10th, a coordinated push began. Every available telescope, every available hour was directed toward 3 Atlas. Observers worked around the clock, stacking short exposures during twilight, pushing instruments to their limits. Engineers repurposed observing modes. Coronagraphs, instruments designed to block the light of stars so that faint nearby planets can be seen, were adapted to block scattered sunlight, allowing slightly longer exposures. Adaptive optic systems, which correct for atmospheric turbulence, were fine-tuned to handle the low elevations and bright skies. The data that came down was noisier than before. The signal-to-noise ratios were lower. But it was data. And every bit mattered. On October 11th, JWST conducted what was likely its final observation of 3 Atlas. The solar elongation had dropped to 45 degrees, right at the edge of JWST's operational limit. The observation window was short, just 2 hours. But it was enough to capture one last thermal map. The hotspots were still there. A, B, and C, flickering and pulsing as before. Hotspot C, the rhythmic one, showed the same 40-minute cycle. No change. No decay. The object was still warm. And it was still anomalous. On October 12th, Hubble took its final images. High-resolution visible light, capturing as much detail as possible about the object's shape and rotation. The asymmetry in the light curve was still present. The small bump that hinted at a surface feature or shadow. One astronomer, staring at the final Hubble image, remarked, "We're losing it. We're watching it slip away, and there's nothing we can do." None. It was true. Observation is passive. You can point your telescope, you can collect light, but you can't reach out and touch. You can't slow it down. You can't ask it to wait. 3. Atlas was leaving, and all they could do was watch. By October 13th, the observation campaign had shifted to a survival mode. Ground-based telescopes pushed twilight observations to the limit, capturing data even when the object was just barely above the horizon, barely distinguishable from the glow of the setting or rising sun. One team in Chile managed to capture a spectrum at an elevation of just 8 degrees, lower than most astronomers would ever attempt. The spectrum was degraded, smeared by atmospheric distortion, but it was there. And it still showed the unidentified features, the anomalous isotopic ratios, the chemistry that shouldn't be there. Every observation, no matter how noisy, added to the growing archive, because after the blackout, that archive would be all they had. On October 14th, a sobering discussion took place among the mission planning teams. If a spacecraft were launched now, today, could it reach 3I Atlas before it faded beyond all hope of intercept? The answer was complicated. The Starship mission, if it were approved, would take weeks to prepare. Even on a fast track, the earliest launch date was late October, perhaps early November. By then, 3I Atlas would be deep in the solar glare, impossible to observe. Navigation would be difficult. Course corrections would rely on models rather than real-time tracking. And there was another problem. The farther 3I Atlas traveled, the faster it moved relative to the sun. Not because it was accelerating, gravity doesn't work that way, but because it was falling away, converting gravitational potential energy into kinetic energy. By the time a spacecraft could catch up, the object would be moving at over 30 kilometers per second relative to the sun. A fast flyby was still possible. A rendezvous where the spacecraft matched velocities and stayed with the object was much harder. It would require more fuel, more time, more risk. The mission planners updated their estimates. A minimalist flyby, $250 as originally calculated. A rendezvous mission, closer to $600 million. $600 million bought you time. Time to orbit, to observe, to analyze. But it also bought you delay, more months of design, more mass, more complexity. The trade-off was stark. Fast and cheap, but fleeting. Slow and expensive, but thorough. No decision had been made yet. The proposal was still winding through bureaucratic channels, waiting for approval, waiting for funding, waiting for someone to say yes. And all the while, the clock ticked. On October 14th, the last day of reliable ground-based observations, a final coordinated campaign brought together telescopes from Chile, Hawaii, Spain, South Africa, and Australia. The goal was simple: capture one last, complete dataset. A final snapshot of 3I Atlas before it vanished. The observations ran for 12 hours, following the object as Earth rotated, handing it off from one observatory to the next, as the sun set and rose around the planet. When the data was processed, it confirmed what everyone already knew. 3I Atlas was still anomalous, still warm, still structured, still defying simple explanation. And now, it was slipping into silence. On the evening of October 14th, one of the team leads sent an email to the broader group. The subject line read, "End of regular observations." The body of the email was brief. As of tomorrow, 3I Atlas will enter the solar exclusion zone for most of our instruments. We will have limited or no observation capability until late November. In the meantime, We focus on analysis of existing data, modeling, and planning for post-glare follow-up. Thank you all for your extraordinary efforts over the past 6 weeks. Whatever this object is, we've done everything we could to understand it. Now we wait. Wait. It was the hardest part. Waiting while the object coasted silently through the glare, invisible, untouchable, carrying its mysteries deeper into the dark. October 9th, 2025. Solar glare had become the enemy. Geometry, not curiosity, dictated the limits of what they could see. And as 3I Atlas slipped toward the sun, the instruments fell silent, one by one, until all that remained were archived photons and unanswered questions. The coming blind spot was not a failure of technology. It was a reminder that the universe operates on its own schedule, indifferent to human desire. This is not science fiction. This is October 2025. Chapter 10. October 14th, 2025. A pulse before the dark. October 14th was supposed to be the end. The last day of observations before 3 Atlas vanished into the solar glare. The final chance to capture data before the weeks-long blackout began. And then, as if aware of its impending disappearance, the object did something unexpected. It brightened. The first hint came from a telescope in Hawaii, part of the coordinated observing campaign scheduled for that final night. The astronomer on duty was monitoring the incoming data stream when she noticed an uptick in the infrared signal. Not dramatic, perhaps a 15% increase over the baseline, but consistent across multiple wavelength bands. She flagged it immediately. Within minutes, other observatories confirmed. Chile saw it. Australia saw it. A space-based infrared satellite, repurposed yet again, saw it. 3 Atlas was getting warmer. Or more precisely, something inside it was releasing more heat. The increase was most pronounced in the region corresponding to hotspot CC, the pulsing hotspot that had been cycling regularly for weeks. But this was different. This wasn't a pulse. This was a surge. Over the course of 2 hours, from 22:00 UTC to midnight, hotspot C brightened steadily, reaching an intensity nearly twice its previous maximum. Then, just as steadily, it began to fade. By 2:00 UTC, on October 15th, the hotspot had returned to its baseline level, the same warm, persistent glow it had maintained for weeks. The surge was over. But it had happened. And it had happened right at the edge of the observation window, right before the object disappeared. On the morning of October 15th, the team scrambled to analyze the data. What had just happened? The simplest explanation was outgassing. A sudden release of volatile material, ice sublimating into gas, escaping from beneath the surface. Outgassing carries away heat, but it also produces a visible coma, or tail. Observers immediately checked for signs of gas emission. They found none. No new spectral lines. No expanding cloud. No tail. Just the thermal surge, sharp and isolated. Another explanation was a phase change. Some materials, when they undergo a transition from one state to another, solid to liquid for example, release or absorb latent heat. If 3 Atlas harbored pockets of exotic ices or chemical mixtures, a phase change could produce a sudden thermal pulse. But phase changes are usually triggered by temperature changes. What would have triggered this one? The object was receding from the sun, cooling gradually, not warming. There was no external event, no impact, no solar flare, unless the trigger was internal. A third explanation, more speculative, was that the surge was intentional. A deliberate release of stored energy, perhaps to shed excess heat before a long period of dormancy, or to signal, or simply because some internal system had completed a cycle and needed to reset. The word intentional made people uncomfortable, but it kept coming up. On October 15th, a thermal modeler ran simulations to see if the surge could be explained by passive processes. She modeled chemical reactions, phase changes, delayed thermal release from earlier solar heating. Some scenarios came close, but all of them required very specific conditions, specific compositions, specific thermal conductivities, specific timings. Fine-tuning, again. One scenario stood out. If 3I Atlas contained a reservoir of chemical fuel, perhaps a mixture of organics and oxidizers, that fuel could undergo a slow, catalyzed reaction, releasing heat over time. If the reaction rate increased suddenly, perhaps due to a buildup of reaction products that shifted the chemical equilibrium, you'd see a surge. But catalyzed reactions don't just speed up on their own. They need a catalyst. And catalysts in space are rare unless they're deliberately introduced. On October 16th, now deep into the solar glare, one last observatory managed to capture a faint echo of 3A Atlas. It was a radio telescope, less affected by sunlight than optical instruments. The VLA, pushing its capabilities, pointed toward the calculated position of the object and listened. They detected a signal. Faint, noisy, but present. And the signal showed a brief increase in intensity, coinciding with the thermal surge observed 2 days earlier. The radio emission had flared, just as the heat had flared. Heat and radio linked again, rising together, fading together, as if driven by a common source. One researcher noted that this was exactly what you'd expect from a power system. When a system generates energy, it produces both heat and electromagnetic radiation. The two are coupled. You can't have one without the other, unless you have perfect insulation and perfect shielding, neither of which exist in nature. It's acting like a machine, she said. Or like a geological process we don't understand, someone countered. Name one. Silence. On October 17th, a meeting was convened to discuss the implications of the surge. Was it significant? Did it change the assessment of 3 Atlas? Some argued it was a final data point, interesting but not conclusive. Others saw it as the strongest evidence yet that the object was not passive. Passive objects don't surge. They cool. They warm. They follow predictable thermal curves. They don't spike right before they vanish from view. It's almost, one scientist said slowly, like it was saying goodbye. The room went quiet. Or, another voice added, like it was dumping waste heat before going dormant. Why would it need to go dormant? To conserve power. If it's an artifact, if it's been coasting through space for thousands or millions of years, maybe it cycles. Active when it passes through a star system, dormant in between. That's a lot of maybes. Everything here is maybes. Fair point. By October 18th, 3 Atlas was effectively unobservable. The solar elongation had dropped below 35 degrees. Ground-based telescopes couldn't reach it. Space telescopes wouldn't point toward it. The object had entered the blind spot. The last confirmed detection came from a space-based coronagraph, designed to study the sun's corona. The instrument, never intended for asteroid tracking, managed to catch a faint, fleeting glimpse of 3E Atlas as it passed through the coronagraph's field of view. The object was still there. Still moving. Still warm, as far as the crude thermal data could tell. And then, nothing. On the evening of October 18th, the observation teams compiled their final datasets. Weeks of images, spectra, light curves, thermal maps, radio profiles. Thousands of individual measurements, stitched together into a portrait of an object that refused to be ordinary. The portrait was incomplete. There were gaps, uncertainties, unresolved questions. But it was more complete than any portrait ever made of an interstellar visitor. And it was strange. One team led, reviewing the final report, wrote a brief summary. 3I Atlas is an interstellar object approximately 500–800 meters in length, rotating every 8.3 hours. It exhibits persistent internal heating, inconsistent with passive thermal models, localized hotspots with semi-regular variability, anomalous spectral features, and isotopic ratios, faint structured radio emission, and a trajectory alignment unlikely to occur by chance. On October 14th, it exhibited a brief thermal surge before entering solar conjunction. The combined probability of these features arising naturally is low, though not zero. Further observations after solar emergence are essential. The possibility that 3I Atlas is of technological origin cannot be ruled out, and warrants serious consideration. She read the paragraph 3 times before hitting send. It was the first official document to state, plainly, and without hedging, that 3 in Atlas might be artificial. The report circulated quietly among senior scientists and agency officials. No public announcement. Not yet. But the conversation was shifting. October 14th, 2025. A pulse before the dark. One last surge of heat, one last flare of radio waves, as if the object were exhaling before a long sleep, or as if it were signaling. A brief, final transmission before silence. We keep returning to the same quiet thought. The universe owes us no simple explanations. But this was more than complexity. This was timing. And timing, in nature, is rarely perfect. This is not science fiction. This is October 2025.